You know, we hear about artificial intelligence and machine learning all the time, right? It kind of feels like magic, but behind the scenes, it's all just powered by math. So today, we're going to pull back that curtain and look at one of its core engines, linear algebra. We're going to see how these simple lists of numbers actually build the foundation for some of the most advanced tech out there.
Okay, take a look at this. You can think of it like the blueprint for machine learning. You've got all these pillars, things like calculus and probability, but what's holding it all up? What's the foundation at the very bottom? Linear algebra. Seriously, it's so fundamental that if you took it away, the whole structure would just fall apart. So today, we're zeroing in on that cornerstone.
So why the big deal? Why is it so darn important? Well, because linear algebra gives us the tools that take complex, messy, real-world data and represent it in a super-structured way, using things called vectors. And once the data is structured, we can build models that learn from it to make decisions. It's literally the language that AI speaks.
And you know, just like with any language, you have to start with the most basic words. Before any of the fancy AI stuff can happen, we first have to describe our data using numbers. And that, my friends, is where vectors come into the picture.
So what is a vector, really? Well, there are a few ways to think about it. A computer scientist might just see an array, a list of numbers. A physicist sees an arrow flying through space with a certain length and direction. But a mathematician sees something way more abstract and way more powerful. It's simply an object that you can add to another one and that you can scale, multiply by a number. That's it.
Now, it's really easy to get stuck on that image of an arrow. But if we stick to those two simple mathematical rules, you can add it and you can scale it, what else in the world can be a vector? Well, the answer might just surprise you.
And this is where that abstract idea really pays off. That row in your Excel spreadsheet, yep, that's a vector. An audio signal, which is really just a long series of numbers, that's a vector too. Even polynomials from your old high school math class, as long as they follow those two simple rules, we can treat them as vectors and use all the powerful tools of linear algebra on them.
Okay, so if vectors are the words of our data language, how do we organize them into meaningful sentences? For that, we're going to need our next big tool, the matrix.
This is such a great way to think about it. A matrix is basically just a grid, a box, a way of neatly organizing a whole collection of vectors all together. It takes all our individual data points, our words, and arranges them into a structured paragraph that actually tells a coherent story.
Let's look at a perfect example. You start with a real-world business problem, maybe a production plan. You end up with this jumble of equations that's just hard to even look at. But linear algebra lets us just pluck out the important numbers and organize them into this really elegant, simple matrix equation, AX equals B. All of a sudden, the mess is gone, and we're left with this clean, workable structure.
But a quick heads up, matrices have some quirky rules. Adding them is simple. It's just like regular numbers. A plus B is the same as B plus A. No problem. But with multiplication, whoa, that's a whole different ballgame. The order you multiply them in is absolutely critical. A times B is not the same as B times A. Think of it like a series of actions. Rotating an object and then stretching it gives you a totally different result than stretching it and then rotating it. This is a super important rule in all of AI.
All right, so we have our language, vectors, and we have our grammar, matrices. So what's the payoff? Well, now we can actually use them to solve problems. Or, as we're about to see, we can find out where the lines cross.
We've been talking a lot about algebra and equations, but let's make this visual for a second. When we say we're solving that AX equals B equation, what are we actually looking for? What does that solution look like?
This is it, right here. Each one of those linear equations is just the formula for a straight line on a graph. And solving the whole system of equations? That's just a fancy way of saying, find the one single point in the universe where those lines intersect. It's this beautiful, simple translation from abstract algebra into geometry.
And if you think about it geometrically, there are really only three things that can possibly happen. One, the lines can cross at exactly one point, which gives you a unique solution. Two, the lines can be parallel, meaning they never ever touch, so there is no solution. Or three, the lines are actually the exact same line, just overlapping everywhere, which gives you infinite solutions. That's it. Every single system of linear equations will have one of these three outcomes. So let's just zoom back out and recap the journey we've been on. We've essentially built this universal toolkit for taking on some really complex problems. We started with the big, complex world of machine learning,
And we asked, what makes this whole thing tick?
And we saw that the very first step is to translate all kinds of data, images, sound, text, whatever, into that one universal language, the language of vectors.
Then, we learned how to organize those individual vectors into these neat grids called matrices, which gives our raw data some real structure and meaning.
And finally, with all that structure in place, we could actually solve for a clear, precise answer to our original problem. We could find that one single point where all the lines intersect.
And this quote from our source material just nails it. Determining the inverse of a matrix is equivalent to solving systems of linear equations. In other words, even these really advanced, complex-sounding operations are, at their heart, just another way of finding that one specific point where everything comes together.
But this leads us to a final, really interesting thought. Linear algebra is perfect for finding the one, single, correct solution. But what happens when our data is messy, like it is in the real world? What if there isn't a perfect answer? What if the lines don't quite cross perfectly? That's when we have to move beyond finding the right answer and start looking for the best possible answer. And that, well, that's a topic for another explainer.